Inside this microchip are approximately 30 billion transistors. And if you were wondering, it's the design of a GPU or graphics processing unit found in the center of a graphics card. How many calculations do you think your graphics card performs every second while running video games with incredibly realistic graphics? Maybe 100 million? Well, 100 million calculations a second is what's required to run Mario 64 from 1996. In order to run the most realistic video games such as Cyberpunk 2077, you need a graphics card that can perform around 36 trillion calculations a second. Imagine doing a long multiplication problem once every second. Now let's say everyone on the planet does a similar type of calculation, but with different numbers. To reach the equivalent computational power of this graphics card and its 36 trillion calculations a second, we would need about 4,400 Earths. When we zoom into a nanoscopic view of this microchip, we find a 3D maze of transistors and layers upon layers of wires with the smallest dimensions of the bottommost layers measuring around 10 nanometers or around 45 silicon atoms. So let's use a thought experiment and pretend that instead of copying transistors and wires, this EUV photolithography system is used to copy the text from a book. If the width of each line of a letter is 13 nanometers, then the word cat would take up around 155 by 240 nanometers. A page of text would be about the size of a red blood cell, and a chapter of a book would be a grain of pollen. Laser pulses run through multiple amplifiers below the cleanroom floor. These laser pulses grow in power and then travel from the subfab using a pathway of mirrors and up through the bottom of the tool and into a chamber called a source vessel. The first laser, called a prepulse, is around 5 kilowatts in power and is targeted at a droplet of tin using a set of actuated mirrors. This prepulse laser turns the tin droplets into a pancake-like shape. The second, approximately 25 kilowatt main laser pulse, which is more than 10 times stronger than the lasers used to cut steel, hits the tin pancake, instantly vaporizing it and turning it into glowing plasma. Within each of the tin atoms, some electrons are ejected and others are kicked up to higher energy states. When electrons drop back down from the 4f to 4d orbitals, 13 nanometer EUV light is produced. Shooting 2 laser pulses at a droplet of tin might seem like a rather obscure process. However, EUV light doesn't naturally occur on Earth, and it's one of the few ways to efficiently produce over 500 watts of EUV light. Additionally, the reason for using tin is that its plasma produces a wide range of wavelengths with a clear peak at 13 nanometers. So, where does the tin droplet come from? Well, over here, a solid ingot of ultra-pure tin is melted and fed into a storage tank and then piped towards a microscopic nozzle. A piezoelectric transducer squeezes the tip of the nozzle, and, due to high-pressure nitrogen inside the storage tank, a droplet of tin is forced out at a speed of 100 meters a second. Next, high-speed cameras measure and calculate the trajectory of the droplet and feed the data to a set of actuated mirrors in order to angle the laser pulses to precisely hit the tin. To control the amount of EUV light, sometimes droplets are skipped by the lasers, and these droplets are captured over here. This process of producing high-speed tin droplets and then shooting them with 2 laser pulses to generate EUV light happens at a rate of 50,000 times a second. Now that we have EUV light, the first mirror, called the collector, focuses all the EUV light to a small hole called the intermediate focus, which only EUV light can pass through. The light next enters into the illuminator, which is composed of the field facet mirror, the pupil facet mirror, and another set of mirrors. These mirrors are so perfectly shaped that there's less than an atom's deviation from the surface. The illuminator takes this EUV light and shapes it into a thin ribbon that has equal uniformity across a well-defined range of angles before it hits the photomask. Using an equal uniformity of light at all angles is critical to imprinting a perfect nanoscopic pattern from the mask via the light and onto the wafer.
Disperse! Nothing to see here, please!